Okay, guys, let's get going here on concept 3. Uh, so, so here's the idea. So at this point, technically, you guys have learned all the skills you need to answer any trig problem that you've come across. Right? You know how to label a right angle triangle correctly. You know how to determine which trig ratio you need to use to solve for your unknown part of the triangle, and then you obviously know how to solve for side lengths in your right angle triangle, and you know how to solve for angles now as well, right? So now we're going to be using all those skills kind of collectively to solve different application or word problems, right? So here we go. So yeah, even in the earliest of times, trigonometry had its purpose to chart the path of celestial bodies or determine inaccessible heights. Mathematicians used trigonometry and without a calculator. Yeah, those old guys with the beards are pretty crazy. In the next few tutorials, okay, we're going to be solving triangles and applying trigonometric ratios. So here we go. So the question says solve triangle x, y, z here, right? So here's what we mean by solve, right? Solve a triangle means to solve for all missing sides and all missing angles, right? So at the end of the day, right, you should know 3 angles and 3 sides, right? Because that's all a triangle has, right? So okay, so based on what we're given here, right, we know 1 angle right here, right? It's a right angle triangle, right? There's our box there, and we know 2 sides. Okay, so at this point here, we need to solve for this side length here, and then what these 2 angles are there. Okay, so now it just says solve, right? So it's kind of up to us to determine how we want to do that. And the reality is we have options for how we want to do that. Okay, so a couple ways we can take a look at it here, right? So to solve for, well, right now to solve for for anything here, right? So understand when we're using trig ratios, we don't want to use, oh, that's the wrong one. We don't want to use this right angle in our trig ratios. And the reason for that is these trig ratios are set up thinking that it's one of the other 2 angles inside a right angle triangle. Okay, so because you're using a trig ratio, it's implied there's a right angle in the triangle, and it's also implied that you're using one of the angles other than the right angle. Okay, so please don't think, oh, right, I'm just going to use this angle and away we go. So we can't do that. So that being said, since we don't have any information, well, what could we do here? Well, right off the bat, I have a right angle triangle where I know 2 out of the 3 sides, right? And well, Pythagorean theorem is still a thing. So if I want to determine the side length here of xz, well, again, right, a squared plus b squared equals c squared, right? So just need to remember that my hypotenuse is always c. So to solve for c, I would have to square root both sides here. So xz would equal to the square root of 6 squared plus 10 squared, right, which would be the square root of 136, which would give me a value approximately, so rounding to 1 decimal place like my side lengths are here, I get 11.7 centimeters. Cool. All right, cool. So there we go. That's 1 side length there. So now we know all 3 side lengths. Now I need to know the other 2 angles here. Okay, so pay attention to this, please, because I think how your strategy to use to solve this is important, right? So whichever angle you want to solve for here first, right, whether it's x or z, doesn't really matter. I'm going to choose x just because. Okay, so I'm going to go, okay, well, x is my reference angle. So now I'm going to determine which trig ratio I'm going to use to solve for it. Well, since technically at this point I know all 3 sides in the triangle, right? So this would be my adjacent. Here's my opposite. Here's my hypotenuse, right? Technically now, since I've solved for my hypotenuse, I know all 3 sides. So technically I could use any trig ratio I want, right? That's fair. However, if this is a test question, it's a good habit to not use side lengths you've calculated if you can avoid it, right? And the reason for that is, well, what if I made a mistake on this side length? We didn't, but what if we did? Obviously my next answer would be incorrect as well, right? So it's always good to go back to what you've been given. So based off of that, I'm going to use these 2 side lengths here. These are the ones that were given to us here. So I'm going to use my adjacent side and opposite. So which trig ratio am I going to end up using here? That's going to be tan. Okay, so I'm going to write tan of angle x is equal to my opposite side divided by my adjacent side here. Now again, I want to solve for my angle, so I need to use the inverse function. So my angle is going to equal to tan inverse of 10 divided by 6. So that's what's going to go into my calculator. And I'm going to get an angle of 59 degrees. We'll round that to the nearest degree. Okay, so then from here, again, we got options, right? So we got all three sides done. I know two of the three angles, so I'm trying to solve for my third one here. So for angle Z, again, we have options, right? So I could set up a trig ratio again, right? And again, I would not use hypotenuse. I would still use adjacent and opposite. However, if I were to do that, right, these would be labeled differently, right? So we have to remember that. So I would still end up using tan, but what would be labeled my opposite and adjacent would be different. Okay, so that's important to know, right? So that strategy is fine. Okay, or, right, we can make our lives easier and realize, well, there's a special property about triangles again, right? This angle plus this angle plus this angle, right? All three angles have to add up to what? They have to add up to 180 degrees, right? So basically then what that means is if I know two out of the three angles, I could just simply subtract them from 180, right? And that would give me whatever's left over would be my third angle there, right? So we end up with an angle here of 31 degrees. Or you could simply, because you're dealing with a right angled triangle, this angle is obviously always 90. So these last two always have to add up to 90 as well, right? Because 90 and 90 makes 180. So you could simply just take 90 and subtract 59 from it as well, and you get the exact same answer there. So how you want to slice that's up to you. All right. So next example here. Solve the following triangle, express all answers to the nearest tenth. Okay, so once again, right, solving means determine all unknown sides, determine all unknown angles here. All right, so here a little bit different scenario, right? We're given a side length and one angle. So for this question, well, we can get angle J pretty quickly by just taking 90 and subtracting 39 from it. Right, so I got an angle here of 51 degrees, right? So that's kind of one you almost get for free, right? Not a whole lot of work involved there, so that's great. So now the question is, well, what are my other two sides here? So since I only know one of the side lengths here, I can't use Pythagorean theorem, right? That you require two of the three sides, right? So I have to use a trig ratio in this case. And even though I've determined what this angle is here, again, just going back to good practice, I might have made a mistake. I'm going to go back to the one that's been given to us, right? So I'm going to use that as my reference angle here. So I'm going to label my triangle accordingly. So here's my hypotenuse. The one given to me is my opposite. And this other side here is my adjacent. Okay, so which side do you want to solve for first? So just to make things easier, I'm going to label this side X. I'm going to label this side Y. Okay, just so we can tell the difference between the two. So I don't know. Let's solve for X first. Okay, so if I want to solve for this side length here, here's my reference angle. Need my adjacent. I know my opposite. So which trig ratio deals with opposite and adjacent? Well, it's going to be tan. So I'm going to set up a tan ratio here. So tan of 39 degrees is going to be equal to my opposite side divided by my adjacent side there. Okay, so again, here's a scenario where what I'm trying to solve for is on the bottom of the fraction. So those two parts are just going to flip. So I'm going to get x equal to 9 over tan of 39 degrees. So I'm going to throw that in my calculator. 9 divided by 10 of 39. I'm going to get 11.1. What units are we dealing with here? Centimeters. Okay, so that's that side length there. Okay, so technically, now I have two out of my three side lengths of my triangle. So I could use these two in Pythagorean theorem, and again, solve for my hypotenuse there. I'm not going to do that because, again, I could have made a mistake there. So I'm going to go back and I'm going to use a trig ratio once again to solve for my hypotenuse here now, right? So 39 degrees is still going to be a reference angle. So now I need to determine which trig ratio deals with opposite and hypotenuse. Okay, and that's going to be sine. So here we go. So sine of 39 degrees is going to be equal to my opposite side divided by my hypotenuse, which I labeled y. So once again, what the side I'm trying to solve for is on the bottom of the fraction. So those are just going to simply flip. So I'm going to get y equal to 9 divided by sine of 39 degrees. Okay, throw that in your calculator, and you're going to get a value of 14.3 centimeters. Okay, great. So, and that's it. We've solved the triangle, right? So here's my two unknown sides. I only had one unknown angle that I got in 2 seconds. Let's go with 8. Okay, but yeah, there you go, done, right? So solved. So now again, if you really want to get fancy, you can kind of check and see, oh, maybe, did I, can I check to see if I did did I do this correctly, right? You can, again, you can use different approaches to kind of double check your work, right? Like let's say I want to well, here's a very easy way to determine if you answered this question correctly, right? Using the angle and these two sides here. So this is what, 14.3. So you could do this. Well, let's pretend. Let's pretend that 51 degrees now becomes my reference angle. Okay, so this is still my hypotenuse. This side here, though, would be my opposite, yes? So let's see. So opposite and hypotenuse is sine, right? So let's see if sine of 51 degrees equals 11.1 divided by 14.3. Now keep in mind, right, these are rounded answers, so it might be slightly off here. Okay, so in my calculator, I'm just going to go sine of 51. Okay, so I get 0.777145 yada yada, and then 11.1 divided by 14.3 is equal to 0.776223. So I mean, to two decimal places to get the exact same value. And even though, again, these are rounded answers here, so I feel pretty good about what we did there. Okay, next example. So a small table has a shape of a regular octagon. Okay, so regular octagon means all the side lengths are the same. So the distance from one vertex to the opposite vertex measured through the center of the table is about 30 centimeters. That's what this right here is showing. There is a strip of wood veneer around the edge of the table. Okay, so veneer, if you're not aware, is like, so all the desks in the classroom have a veneer finish to them, right? So basically what that means is the meat and bones of the desk is just made from cheap particle board, and then they glue this finish on the top of it that's called a veneer. So obviously you're not going to get splinters with all this particle wood when you're writing your work, right, in class, right? So it gives it kind of a nice finish, a nice smooth finish there, and it's a lot cheaper than making a desk out of like a pine or an oak or something like that, right? So it gives it a nice wood finish, but it's not really real wood. Anyways, okay, so this wood veneer finish is being put around the edge of the table, right? So in other words, you're looking at this from kind of a bird's eye view of the table, and then the veneer finish is going to go along the edge of this table, right? You can kind of think of it like a poker table if you want, right? So each person's going to sit at each one of the side lengths, right? So, okay. So that's that. So the question is, what is the length of this veneer to the nearest centimeter? So first things first, we have to relate what's being asked to us to kind of properties of shapes and like kind of relate it to math things that we know, right? Well, again, if this veneer goes along all the edges of this table, what about this shape are we trying to calculate? Well, this whole distance along the whole outside of the shape is the perimeter of the what do we got here? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, sorry, the perimeter around this octagon. Okay, cool. So how the heck do you figure out the perimeter of an octagon, right? I don't really remember going over that earlier in the unit. I don't know if there is a formula per se that's really been gone over. I'm sure you can Google one. Okay, but understand here, right? This is a trigonometry unit, right? So you're going to be dealing with right angle triangles. So when in doubt, trying to look at it from the lens of right angle triangles, right? So I don't see any right angle triangles here. So let's see what we can come up with. Okay, so here's a couple things to understand. Okay, so so normally in this situation, I would actually give you some time in class to talk about this in a group, and I'd literally probably give you 5-10 minutes to see what you guys can come up with here. So unfortunately, we're not going to be doing that. So here's how this works. Okay, so again, the whole distance from here to here is 30, right? So that was given to us for a reason. So it's fair to say if that whole distance from there to there is 30, half of that, better color, okay, half of that is going to be 15. Right, makes sense. And since it's a regular polygon, that means that this distance here would also be 30, meaning that this distance just here, this half of it, right, from this vertex to the center, would also be 15. All right, so now what I want to do is I'm going to take this triangle, I'm going to redraw it here, just so it's a little bit easier to work at. So here's what we have so far. I got this side of 15, this side's 15. Why does this matter? Because I'm dealing with an octagon, not a non-right angle triangle. Okay, here's what's important again, right? So to determine the perimeter, right, it's all these flat parts here, right? And since it's a regular polygon, all of these are the same length. So that would mean that if I can figure out what the length of one of these sides are, instead of looking at it all at once, right, I can use that to my advantage, right? If I could determine what one of these side lengths are, I would simply just need to multiply it by 8, because it's an octagon. There's going to be 8 of them, and that's going to be the whole distance around the table. All right, so that's why I'm focusing my attention now just on one triangular slice, if you will, right? Because I know all of these are the exact same triangle because it's a regular octagon. Okay, so I'm focusing on that. All right, so great. All right, well, I could do this. Clearly, this triangle is not a right-angled triangle, but I do know that it's an isosceles triangle, right? I know it's an isosceles because I know I have two side lengths here that are going to be the same. Meaning, if I drew a vertical line straight down the middle, I basically split this triangle into two equal halves, and this vertical line I'm drawing would make a right-angled triangle. Okay, that's great. And now what I could do is I could focus my energy on determining what this side length here would be. So let's call it x, right? So that would be basically half, right? Here's x right here, right? This would be half of that one edge length that I've been looking at. Okay, so we're narrowing our view even smaller now. Okay, great. So now I have a right angle triangle. I know my hypotenuse is 15. I want to know what that side length is. Now the issue here obviously is I don't know what any of my angles are. Okay, so now let's go back to big picture here. Let's look at the whole table as a whole. All right, so, and I'm just going to erase some stuff here because it'll be easier for you to look at now. Okay, so if I were to, and you guys know the answer to this, if I were to draw a circle, right, around this shape, right, what angle does a circle make? Well, it makes 360 degrees. All right, well, if I took that same circle and I split it into 8 equal slices, right, you think of like a pizza if you want, right, 8 equal slices, well, 360 divided by 8 is going to give me, I can't remember off the top of my head, 45 degrees. Knew it. 45 degrees, right? Meaning this is 45, this is 45, this is 45, this is 45, this is 45. Right, on and on. Okay, now let's go back to our triangle we had over here, meaning this whole angle here is 45 degrees. Okay, great. Well, I'm not using that whole angle anymore in my right angle triangle below here, the purple one. I'm using half of that angle. Well, what's half of 45 degrees? 22.5 degrees. All right, so now by again drawing those conclusions, right, taking it back from a zoomed out view back into a zoomed in view here. Okay, now I have enough information where I have an angle on my triangle, I have a known side, I can determine what this unknown side is here. Okay, cool. So 22.5 becomes a reference angle. 15 becomes my hypotenuse. X is my opposite side. So the question is, which trig ratio do I need to solve for my unknown side here? The answer is sine. Okay, so here we go. So sine of 22.5 degrees is going to be equal to my opposite divided by my hypotenuse. Okay, now to solve for x, I need to multiply both sides by 15. So I'm going to get 15 times sine of 22.5 degrees. So after I put that in my calculator, I get a value of 5 point. Now I'm going to leave this value in my calculator here. I'm not going to do any rounding yet because this is not my final answer. Okay, so to determine the actual edge length of the veneer now, right, or my perimeter, here's what I need to do. I need to take that distance that I have here, right, that's half of an edge length. And so basically what's going to happen, I'm leaving this value, whatever the full number is in my calculator, I'm just leaving that in my calculator, okay? And well, now 8 of these full side lengths makes the whole perimeter. So if I have only the length of half of one, that means I need double the amount, right? So I'm going to need 16 of them to get my full perimeter. So I'm going to take that, multiply by 16 in my calculator, and then I'm going to be rounding this value because this is at the end of the day what the question's asking, and I get a value. Sorry, and the question says to the nearest centimeter, right? So in other words, that's saying to the nearest unit. So that means no decimals, right, when you're rounding here. Okay, so this will get rounded to 92 centimeters. Okay, great question. Very challenging question. Fair, but definitely a tough one nonetheless. Okay, so it might be a good idea to kind of rewatch that one if you want. Just about the process that I used to solve that, right? Kind of what my thinking was there. Okay, next and last example here. So, a helicopter leaves its base and flies 35 kilometers due west to pick up an injured person. Um, and then it flies 58 kilometers due north to the hospital. When the helicopter is at the hospital, how far is it from its base to the nearest kilometer? Okay, so the obvious thing that's missing from this problem is a diagram, right? So before we kind of work through this, let's try and figure out what the diagram is here first, right? So we've got a helicopter, leaves its base and flies. So before we even really talk about this, let's remember this, right? Kind of think of a compass here, right? You got never enter smelly washrooms, right? Northeast, southwest. Okay, so we're going to use that idea to help us with our directions, right? So first, this helicopter is going to fly 35 kilometers due west. So due west means in a west direction here, okay? So, and it's from the base. So what I'm going to do is I'm going to start with B as my base. So from there, I'm going to fly due west for 35 kilometers, okay? They pick up some injured person, okay? So that's where the person is, sure. And then from there, they fly 58 kilometers due north. Well, due north is exactly perfectly vertical. There we go. This is the 58 kilometers to the hospital. So here's the hospital there, right? Now the question's saying when the helicopter is at the hospital, that's this part right here, how far is it from the base to the nearest kilometer? So when you're asked how far something is, right, it's always going to be the straight line distance from one spot to the other. Okay, so little teaser, this kind of concept here, if you're in a physics class, you're actually talking about what we call vectors. Okay, so and this is and that red arrow I drew is your resultant vector, but that's again an aside, little fun fact for you there. So anyways, right, so you see, right, it's, you can make the conclusion, well, if I go west and then I go north, well, that makes a right angle, right? So my diagram here now obviously has a right angle triangle in it. That's good because I'm dealing with the trig unit. It's all right angle triangle stuff, okay? So that's good. Now we're just simply asking, okay, well, what's the hypotenuse of my right angle triangle? Okay, so now in this instance, we don't have any angles aside from our right angle, so we actually can't use a trig ratio, right? So the only other strategy we have to use is Pythagorean theorem, right? So here's a right angle triangle. I know 2 of my 3 sides, so let's solve for what hypotenuse is here, right? So I'll just call this x, okay, for my distance there, right? So x, so again, right, your a squared plus b squared equals c squared. To solve for hypotenuse, I'm just going to square root both sides there, right? So x is going to be equal to the square root of 58 squared plus 35 squared. Okay, and I'm going to get a distance of 67 to the nearest kilometer. So you get 67.7, roughly that rounds to, which would mean to the nearest kilometer, right, or nearest unit would be 68 kilometers, right? And again, that means nearest kilometer means no decimals, just like it nearest a centimeter meant no decimal. Okay, so that's your distance there. Cool. Last part here, so when the helicopter is at the hospital, what is the measure of the angle between the path it took due north and the path it will take to return directly to the base? So what is that angle in there? All right, no big deal. So once again here, if I can avoid it, I'm gonna try and not use this distance here that we've calculated, right? I'm gonna try and just use these two here. So then basically I have my right angle triangle, 58, 35, and then there's my theta I'm trying to solve for, right? Okay, so here I have my opposite side, here's my adjacent side, so which trig ratio deals with only opposite and adjacent? That would be tan. So tan of theta is going to be equal to my opposite side divided by my adjacent side. So now here's a situation where I'm solving for an angle, right? So I'm going to use the tan inverse, so theta is going to be equal to the tan inverse of 35 over 58. Okay, so to the nearest degree, right, again, so no decimals, we get an angle here of 31 degrees. Okay, so you may notice in the notes there on D2L, I use like tan H instead of theta. Why? Because, well, here's angle H right there, so it's irrelevant. It's 6 of one, half a dozen the other. It's just something that I'm using to represent that value, right? So it's just a notational difference. Okay, not the process is exactly the same though. Okay, so all right, there's concept 3. So again, right, when in doubt, always, obviously because it's a trig unit, always think of the problem in terms of right angle triangles if you can, right? If you try to zoom in on the problem to smaller and smaller portions, right, to try until you get to a right angle triangle. And when you do not have a diagram, obviously drawing one is going to be important, right? So how do you get better at drawing diagrams? By working on these types of problems, right? So again, these word problems are going to be the last are going to be in the homework assigned for this lesson. Okay, these word problems are going to be the last ones in the section. Okay, right? So again, I've mentioned this before, right? They're the ones that are more wordy, are the ones that students generally skip over, right? So please don't do that. Put in the work, because I think this is the most challenging part of this unit. It's not the actual working through the ratios, it's this part here, right? Actually applying it, right, to kind of real life type problems here. All right, so that's the end of concept 3 again. So start working away out of your textbook for this, and again, shoot me up with that's probably not a good phrase to use. Hit me up, that's a better word. Hit me up with email or text if you have any questions. Talk to you next time.